7,000 miles from the nearest city, under a sky that never fully brightens for half the year, a wall of ice the size of Florida is coming apart from the inside. Scientists have a name for it that sounds almost too dramatic to be real until you understand what it's actually capable of. They call it the Doomsday Glacier. Its real name is Thwaites, and for the better part of 2 decades it has been quietly rewriting what researchers thought they knew about how fast an ice sheet can fail. Now, new data pulled from satellites, underwater robots, and ocean sensors that have spent years crawling beneath the ice itself is showing something that has monitoring teams abandoning their normal schedules. What they found isn't a slow, predictable retreat. It's a system that may be closer to a tipping point than anyone was willing to say out loud until now. To understand why a single glacier at the bottom of the world can dominate headlines and unsettle climate scientists more than almost anything else on the planet, you have to understand what Thwaites actually is. It isn't just a big chunk of ice. It's a plug. Thwaites sits at the edge of West Antarctica, and behind it is a basin of ice that, if it were ever fully released into the ocean, holds enough water to raise global sea levels by over 2 feet on its own. That's Thwaites alone. But Thwaites doesn't fail in isolation. Glaciologists have long warned that Thwaites acts like a cork in a bottle for a much larger section of the West Antarctic ice sheet. Pull the cork, and the ice behind it doesn't just melt. It can be pulled out to sea in a chain reaction that some models suggest could eventually contribute more than 10 feet of sea level rise over the coming centuries. 10 feet doesn't sound like an abstraction when you remember that most of the world's largest cities, Miami, Shanghai, Mumbai, New York, Jakarta, sit within a few feet of current sea level. For years, the working assumption was that this kind of collapse, if it happened at all, would unfold over centuries, slow enough that it stayed a problem for future generations to manage. That assumption is exactly what the latest wave of research is challenging. Teams operating in the region deployed autonomous underwater vehicles, essentially torpedo-shaped robots, to swim directly beneath the glacier's floating ice shelf into a zone humans have never been able to reach directly. What they mapped down there was not what anyone expected. Warm ocean water, water several degrees above freezing, is not just lapping at the edges of Thwaites. It is being funneled directly into the cavity underneath the ice shelf through channels and fractures, attacking the glacier from below in places that satellites on the surface can't even see. This is the part that should concern anyone paying attention. The melting isn't happening the way older models predicted, evenly and gradually along the underside. It's happening unevenly, aggressively, concentrated in specific corridors where warm water is essentially carving staircases into the ice. That matters because of a mechanism scientists refer to as marine ice cliff instability. Here's the simple version. Thwaites ice shelf. The floating tongue of ice that extends out over the ocean acts like a brace, holding back the much taller ice cliffs further inland. As the ocean eats away at that floating shelf from underneath, the brace weakens. Eventually, it can fracture and break away entirely. When that happens, it exposes towering ice cliffs in places over budget-breaking heights, directly to the open ocean. Ice cliffs above a certain height cannot support their own weight once nothing is holding them up from the front. They don't melt. They collapse, physically shatter under their own mass, in a process that, once it starts, can become self-sustaining. Each collapse exposes a new cliff face, which becomes unstable, which collapses again. It's the geological equivalent of pulling a supporting wall out of a building and watching the floors above it come down one after another. The newest data suggests this process may already be further along than the last generation of monitoring equipment could detect. Fracture zones that researchers were tracking as slow-moving, multi-decade features have shown measurable acceleration within a much shorter window. Grounding line retreat. The point where the glacier lifts off the seafloor and starts floating. Has moved inland at rates that, when extrapolated, put some of the most aggressive collapse scenarios back on the table. Scenarios that, only a few years ago, were treated as the unlikely outer edge of the range, the kind of thing you mention as a worst case and move past quickly. Now they're being discussed as plausible. None of this means the glacier is going to vanish next year, and no credible scientist studying Thwaites is claiming otherwise. What has actually changed is the confidence interval. The gap between the best case and worst case timelines has narrowed, and it's narrowed in the wrong direction. Where earlier assessments left room for Thwaites' major structural collapse to be a late century or even next century event, the newest observations are forcing some of the most conservative voices in the field to admit that a scenario measured in decades rather than centuries can no longer be ruled out. That's an extraordinary admission in a field built on caution and measured language. The response from the scientific community has been to do the things scientists always do when the picture starts changing faster than expected. Watch closer, model more, and refuse to speculate beyond what the data supports. Research stations in the region have expanded monitoring schedules. More sensor arrays are being planted beneath the ice shelf to track exactly how warm water is moving through those fracture channels in real time. Satellite passes over the region have increased in frequency, looking for the kind of surface cracking that would signal a major shelf break is imminent. This isn't panic. It's the scientific equivalent of moving from routine checkups to intensive monitoring, because the patient's vital signs just changed in a way nobody was expecting to see this soon. And here's the part that connects a remote ice shelf 7,000 miles from anywhere to a life that has nothing to do with Antarctica at all. Sea level rise from Thwaites wouldn't stay in Antarctica. Ocean water redistributes globally, and a glacier's contribution to sea level doesn't respect coastlines or borders. If even the shelf collapse phase of Thwaites accelerates the way current data suggests it could, coastal infrastructure that engineers have built around century-long planning horizons, seawalls, drainage systems, flood insurance models, could find themselves obsolete decades ahead of schedule. Cities that assumed they had until 2150 to adapt could be looking at real, measurable impact by mid-century instead. That's the gap between the old projections and what the new data is suggesting. Not a difference in what eventually happens, but a difference in how much time there is to prepare for it. What makes Thwaites uniquely dangerous, compared to other ice loss happening around the world, is this feedback loop between the ocean and the ice geometry itself. Most glacial melt is a relatively linear story. Warmer air, warmer water, more melt, repeat. Thwaites carries the added risk of runaway mechanical collapse, where the physics of ice cliffs failing under their own weight can outpace the climate trends driving the melt in the first place. Once marine ice cliff instability truly engages at scale, it isn't governed primarily by how fast the planet is warming anymore. It's governed by gravity and the structural limits of ice, and those don't slow down for anyone. Scientists studying the region are careful to note what they don't yet know. They don't know with certainty exactly when a full shelf break might occur. They don't know if the warm water intrusion detected this cycle will continue at the same intensity or if it represents a temporary spike. What they do know is that the assumptions built into a decade of prior modeling, that Thwaites had time, that the worst outcomes were centuries away, are being actively re-examined in real time based on direct observation rather than projection. That distinction matters. This isn't a computer model predicting the future. This is a robot, physically underneath the ice, recording exactly what's happening right now. For now, the monitoring continues. More underwater missions are planned. More sensors are going in. And for the first time in the 2 decades scientists have studied it, Thwaites is being watched not as a long-term research subject, but as a system that could cross a threshold sooner than anyone is fully prepared for. Whether that threshold is 5 years away or 50, the message from the people who study it closest hasn't changed. But the urgency behind that message has. And that shift from patient long-term monitoring to close, active watching, is itself the warning worth paying attention to.